The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
Phase diagram for water. Let's begin here with a definition. Phase diagram is a graphical depiction of how temperature and pressure impact the stability of the physical states of a substance, and in our case that's going to be water. Looking here at figure 4.10, here we can see where water is stable in various phases at various pressure and temperature combinations. Meaning here we're going to have solid ice, here liquid water, and here we would have a gaseous water vapor. Now these lines here, they're also significant as well. If we take a look here at this first line, we'll consider this to be solid line A. At this point here, the solid ice and the gaseous water vapor are going to be at equilibrium at these pressure temperature combinations. Furthermore, solid line A here gives us all the different sublimation points for water at the different pressure and temperature combinations. Now, as we go up this line here and we reach our first bullet here, at that point there, that's going to be the triple point. That's going to be the triple point as such. Now, what is the triple point? Well, the triple point is where all three phases coexist, meaning solid ice, liquid water, and our gaseous water vapor are all going to be in equilibrium. Now, if we go up from the triple point here, where we have another solid line, which we'll just designate here as solid line B. Now, at solid line B, here we're going to have solid ice and liquid water in equilibrium as such. Now, furthermore, at solid line B, these are going to be all the different melting points, right? These are going to be all the different melting points for water at different pressure temperature combinations. And if we take a look right here, that's going to be our normal melting point at 1 atmosphere and 0 degrees Celsius. Furthermore, most substances here are going to have a positive slope. However, for water, if we notice, this line is going to give us a negative slope. And that's due to the fact that frozen water is less dense than liquid water. Now, as water molecules freeze, the three-dimensional networks created by hydrogen bonds between the molecules also freeze as well, with considerable empty space. And as we increase the pressure here, right, at constant temperature, that ice will begin to melt. And a great example of that is given here. If we take a look at, a great example of that is given here. If we take a look at our ice skater, the skate is going to exert a great amount of pressure onto the ice, and that ice will begin to melt. The forming liquid will serve as a lubricant between the ice and the skate, providing that skater with graceful mobility. Now, getting back to our slide over here, the solid line right here, which we'll designate as solid line C, that's going to signify all the different points where liquid water and gaseous water vapor are going to be in equilibrium at different pressure and temperature combinations. Furthermore, these are going to be all the different boiling points for water at different pressure and temperature combinations here. Now, if we keep going up our line here, we reach this point here. That's known as the critical point. That point there, that's known as the critical point as such. Now, the temperature at the critical point is the critical temperature, and the pressure is going to be the critical pressure. And furthermore, if we look here at the critical temperature, any pressure past the critical temperature is no longer going to be able to liquefy that gas. And furthermore, at the critical pressure, no matter how much we increase the temperature here, that liquid, we can no longer vaporize it. Instead, we get this interesting, we can say, fluid here known as the supercritical fluid. And it's not really a true gas nor a true liquid. It's actually quite astonishing. You can YouTube it if you like, if you desire to see what the fluid actually looks like. But for the rest of us, let's continue now.